I will be taking the portion today, that the topic today for the lecture is radioactivity and nuclear decay. And I'll take this lectures on the first part of it. I will be discussing what is radioactivity, why are some isotopes radioactive while others are not. Then I will touch upon natural radioactivity, artificial radioactivity, and the laws that govern radioactivity. Also, there are some type of equilibria which I will be discussing. Okay, so all of you know that the phenomenon of radioactivity was discovered by Henry Becquerel in 1896, and we will be celebrating the 125 years of this discovery in this year 2021. In fact, we have arranged a webinar on 1st of March, the day the phenomenon was discovered, and all of you are welcome to join this webinar. And you know that the discovery of radioactivity was in the form of blackening of the photographic plates kept in the dryer by Professor Becquerel. In the same dryer, the uranium compounds were kept, and he was studying the fluorescence of uranium compounds. There was no light in that place. So even in the dark, the photographic plates got blackened, led him to conclude that the compound of uranium emits some invisible radiations which are going to blacken the photographic plate. And all of you know that later Madame Curie and Pierre Curie found out some more radioactive elements in that salt of pitch blende, like polonium and radium. So what is the radioactivity? Radioactivity is the spontaneous disintegration of atomic nuclei in which the ionizing radiations like alpha, beta, and gamma are emitted. This ionizing radiations ionization is an important part of these radiations, because that is what we will be discussing subsequently. Radioactivity is an atomic phenomenon. It does not depend upon the chemical state of an atom. And so you will find whatever is the chemical form of an atom, for example, uranium metal, uranium oxide, or any compound of uranium, the half-life will not change. So radioisotopes half-lives are independent of their chemical state, though there are cases where the atomic electrons are involved, for example, in electron capture or internal conversion. There, if you change the chemical environment, because of the electron density changes in different compounds, there has been a very, very small change in the half-lives of the order of 0.1% or so. So to that extent, the chemical state might change the half-life of the radioisotope. Okay, so as I just mentioned, the phenomenon of radioactivity was discovered by Henry Becquerel in 1896 in the uranium compounds, particularly the ore of the uranium pitch blende. And later on in 1898, Madame Curie and Pierre Curie discovered radium by separating radium from the pitch blende. Radium 226 has the half-life of 1600 years, and to honor the discoverer of this element, the unit of radioactivity, one of the units of radioactivity is in the name of Curie. Activity equivalent to 1 gram of 226 radium is actually 1 Curie. Later on, Rutherford and Soddy studied in details the phenomena of emission of alpha, beta, and gamma radiations from different radioisotopes and formulated the group displacement laws which govern how the mass number and atomic number change whenever there is a change, whenever there is a radioactive decay. So all of you know that uranium-238, when it is decaying by an alpha particle, the mass number is changing by 4 and the atomic number is changing by 2. In the case of beta minus decay, for example, 239 uranium, when it undergoes beta minus decay, the mass number remains the same, but the atomic number increases by 1. In the case of beta plus decay, where a positron is emitted or a competitive mode electron capture is happening, the mass number remains the same. With the atomic number, I think there is a problem. Okay, sodium 22 decaying by neon 22, so atomic number is decreasing. In the case of gamma ray, the gamma decay actually is not the decay from the ground state of a nucleus, but it is like when we leave a nucleus in excited state. When a nucleus is found in an excited state, it will emit gamma ray to come down to ground state. So gamma decay essentially is the de-excitation of the excited nuclei, like the excited atoms decay by X-rays, excited molecules decay by UV visible radiations, excited nuclei decay by gamma rays. I have also shown here the actual process that happens in beta minus decay, wherein a neutron is converted to a proton and electron and a antineutrino also emitted. It is a 3-body process, and because of the emission of 3 particles, the beta particles have a continuous spectrum. Okay, so how do we measure the radioactivity? How do we quantify the amount of radioactivity that I have tried to explain? So activity essentially is number of atoms decaying per unit time or disintegrations per second. So when the number of atoms are decaying, it is minus dN by dt. Number of atoms decaying per unit time is proportional to the number of atoms at that point of time, and you replace the proportionality sign with a constant lambda, then this is the activity is equal to n lambda. And activity is measured in terms of becquerels. 1 becquerel is 1 disintegration per second, and 1 curie is 3.7 × 10 becquerels. As I just mentioned previously, that this unit refers to the activity due to 1 gram of 226 radium, which has got a half-life of 1600 years. So if I want to calculate how many becquerels is 1 curie, I calculate the number of atoms in 1 gram of 226 radium. So 1 gram, 226 gram of radium contain Avogadro number. So this in 1 gram you will have this many atoms into the half-life, into the lambda decay constant, 0.693 divided by half-life, 1600 years into 365 days per year, 24 hours per day, and 3600 seconds per hour. So that is how you can substitute these numbers and find out this amount will come to 3.7 to the power 10 becquerels. We also talk about millicurie and microcurie. Accordingly, you can see that 1 millicurie 3.7 to the power 7 becquerels, 1 microcurie 3.7 to the power 4 becquerels. Now let's discuss some fundamentals. Why do nuclei decay? So it is very simple. Anything you have in an excited state, or if you have a pathway to decay, this is the thermodynamic instability of a nucleus that is the cause of its disintegration. It is the inherent thermodynamic instability. For example, you have the water stored in a dam at a higher height. The moment you open the floodgates, the water gushes down because water at the dam has got higher potential. Similarly, a nucleus having higher mass than another nucleus has a higher potential, and if there is a pathway, then this nucleus will decay. The underlying principle is that the mass of the parent atom has to be more than that of the products. Just see an example here. Phosphorus 32 undergoing beta minus decay to sulfur 32, in the process emitting a beta minus and an antineutrino. Now let us see the mass. What is the Q value for this reaction? So I have tried to put the masses. These are not actual masses, these are the mass defects. Okay, now they are the actual masses in atomic mass units. So phosphorus 32, as Dr. Reddy was mentioning the other day, the atomic mass of phosphorus 32 is 31.97 something, minus that of sulfur 32. So this is 0.001834 atomic mass unit. And the energy equivalent of this atomic mass unit is, you multiply by 931 MeV, you get 1.705 million electron volts. So this is positive. So that means there is the phosphorus 32 mass is higher than that of sulfur 32. Hello. I'll give later on. I'll talk later on. So there is a decay of phosphorus 32 to sulfur 32 because phosphorus 32 has a higher mass than sulfur 32, and there is a mode of decay possible, that is beta minus. And this energy, we call as the Q value, is shared between three particles. Now we will be talking about energy of radiation in terms of electron volts many a times in our lecture. So 1 electron volt is 1.602 10 power minus 12 hertz. 1 electron volt is actually the energy gained by an electron when it is accelerated to 1 volt potential. Unlike the chemical reactions which can be reversible, radioactive decay is irreversible. So, radioactive decay is irreversible because there is a large positive Q value, and so you cannot have irreversibility. Dr. Reddy also talked about nuclear mass. Nuclear mass is given in terms of the masses of the constituent nucleons like proton and neutron and the binding energy. So when the Z protons and N neutrons combine to form a nucleus NZA, energy equivalent to B is released. So the binding energy essentially is the energy released when the constituent nucleons combine to form a nucleus, or it is the energy required to break the nucleus into constituent nucleus. Okay, so the energy released when Z protons and N neutrons combine to form a nucleus, then that is the binding energy. Higher the binding energy, lower is the mass and more stable the nucleus. Now, as we are discussing the phenomenon of radioactivity, let us discuss a little bit more details. Why some isotopes are radioactive while others are not. And we'll come to one conclusion that the neutron to proton ratio is an important parameter to define the stability of a nucleus. I've given you some examples here. Isotopes of carbon like 11, 12, 13, and 14. Carbon 12, 6 protons, 6 neutron. Carbon 13, 6 protons, 7 neutrons are stable. The moment I add one more neutron to carbon 13, we have carbon 14. And this carbon 14 undergoes beta minus decay to nitrogen 14. I take out one neutron from carbon 12, I have carbon 11, and this carbon 11 is beta plus active, going to boron 11. So you can see here, if you alter the neutron to proton ratio, you increase the neutron to proton ratio, we get beta minus active nuclei. If you decrease the neutron to proton ratio, you get beta plus active nuclei. Similarly, cobalt 59 is stable. We add one neutron, we get cobalt 60 with beta minus active. If you remove one neutron, we get cobalt 58, which is either beta plus or electron capture. So the neutron to proton ratio of a nucleus is a very important parameter in governing its stability. So atoms are stable if their neutron to proton ratio is in a particular range. So why some isotopes are radioactive and some are not? Because those which are stable, they have a well-defined neutron to proton ratio. Those which are radioactive, they have either higher than the stable ones or lower than the stable ones. Okay. The natural radioactivity, all of you know, there is activity in nature from the time immemorial. Now there are two ways of looking at the radioactive isotopes which are available in nature. One type of radioisotopes are which have the half-life of the order of age of the Earth, and therefore, though they are decaying, they are still present in the Earth's crust because their half-lives are very, very long. For example, 238 uranium having half-life 4.9 billion years undergoes alpha decay, a series of alpha and beta decays right up to and end up with the stable isotope 206 lead. And you'll see here all members of this chain can be classified into 4n plus 2. The mass numbers can be written as 4n plus 2, where n is an integer. And like this series, there are two more series, 4n plus 3, starting from 235 uranium, ending with 207 lead, and 4n series, starting from 232 thorium, ending with 208 lead. Similarly, potassium 40 also has very long half-life, and it is decaying to argon 40. On the other hand, we have carbon 14 having half-life 5,700 years, tritium having half-life 12 years. Though the half-lives are very short compared to age of the Earth, they are present in Earth's atmosphere because they are being continuously formed by interaction of cosmic ray neutrons with the nitrogen, which is abundantly available in the atmosphere. So, in fact, our body contains carbon 14, tritium, and even potassium, because our body contains potassium, and potassium contains this isotope also. So, wherever there is natural potassium, potassium 40 also available. Then, in 1934, Irene Curie and Frederick Joliot were the first to find out that you can also produce radioisotopes in the laboratory by artificial means. They bombarded aluminum-27 with alpha particles and found out that phosphorus 30 is beta plus active and undergoing beta plus decay to silicon 30. This was the first reaction where the products were found to be radioactive in a nuclear reaction. And after that, there have been so many radioisotopes produced, so much so that the number of radioactive isotopes is an order of magnitude higher than the stable isotopes. The half-lives of these radioisotopes ranges from 10 to the power 15 years to microsecond. So now you can produce radioisotopes in large numbers. Depending upon the requirement, you can produce a particular radioisotope. Okay. So now let us discuss little more details into the laws that govern the radioactive decay. As I mentioned in the beginning itself, that the rate of disintegration of a radioisotope can be given in terms of the decrease in the number of atoms per unit time, and this rate is proportional to the number of atoms at that point of time. And if you remove the proportionality constant, then it becomes minus dN by dt equal to lambda n, which is a first order equation. And the solution of this equation, all of you, I'm sure, know it. That is the number of atoms at any point of time equal to the initial atoms into e raised to minus lambda t. So the atoms of a radioactive isotope decay exponentially with time. And when the number of atoms have become half, that means when n becomes n0 by 2, that time is called as the half-life. So if you substitute this n equal to n0 by 2 in this equation, then you get t equal to t half, and so t half will be equal to ln2 by lambda, or you can say ln2 is 0.693 by lambda. So this is the relationship between t half and the lambda decay constant. Okay, so now let's go a little more into details of radioactive decay chain. Radioactive decay chains are when you have a radioactive isotope decaying to another isotope which also happens to be radioactive. Like I have written here, A going to B, and B going to C. So initially at point T equal to 0, the number of atoms of parent is N1 0, and there is no daughter element. So we talk about parent and daughter in radioactive decay. So this N2, number of atoms of B, is 0 in the beginning. And so the decay of the parent isotope A is given by N1 equal to N1 0 e raised to minus lambda 1 T. And the daughter product B is growing from A, but it is decaying to C. And so the rate of growth of the daughter dN2 by dt can be given in terms of rate of formation N1 lambda 1 from the parent minus rate of decay, that is the N2 lambda. So now this is a differential equation which has got you can N1 and N2. You can substitute N1 using this equation, N1 0 is 1 lambda t, lambda 1 t, and so you get this equation, N2 dN2 by dt plus N2 lambda 2. We separate the variables equal to N1 0 lambda 1 e raised to minus lambda 1. This should be minus lambda 1. And now this solving this differential equation is you multiply by an integration factor e raised to lambda 2t both sides. So you can see here you multiply by e raised to lambda 2t here, here, and here, and then solve it. So this becomes actually the differentiation of n2 e raised to lambda 2t, which you integrate, then it becomes n2 e raised to lambda 2t, and the other side will become n lambda 1 by lambda 2 minus lambda 1, n1 0 e raised to lambda 2 minus lambda 1 t plus c. So if you want to find out the activity in terms of instead of number of atoms of B, I multiply this by lambda 2, the n2 lambda 2 becomes activity of the daughter atom A2. So A2 becomes N2 lambda 2, and it will be here. So this lambda 1 is not, it has to be lambda 2 here. Lambda 2 by lambda 2 minus lambda 1, A10, the parent activity, e raised to minus lambda 1t minus e raised to minus lambda 2t. So this essentially gives you the activity of the daughter atom B at any point of t from a freshly purified parent having activity A10. Now, depending upon the half-lives of parent and daughter, you can have different scenario, and we call them different types of equilibria. So if lambda 1 is less than lambda 2, so as I mentioned previously, if lambda 1 is less than lambda 2, that means the half-life of parent is more than that of daughter. And so the daughter will attain equilibrium with parent activity, and after some time will decay with the half-life of parent. I will explain it in more details in subsequent slides also. It is like, you have two tanks. One tank is empty to another tank, and so depending upon the diameter of the tap, inlet tap and outlet tap, there could be a steady state in the second tap, or there could be no steady state. Whenever there is a steady state, we say it has reached an equilibrium. So, depending upon the half-lives, we have either a transient equilibrium or a secular equilibrium, or there is no equilibrium. When we have a transient equilibrium, means the half-life of parent is about 10 times more than that of daughter, or the decay constant of parent is 10 times less than that of daughter. Give you an example here. 140 barium having the half-life of about 12 days decays to 140 lanthanum having a half-life of about 40 hours, and it's decaying to 140 cerium, which is stable. So I will discuss the decay and growth of parent and daughter subsequently. In the case of secular equilibrium, the parent half-life is very, very large compared to that of the daughter, or the decay constant of parent is very small compared to that of the daughter. Giving an example here, 144 cerium having one half-life of 184 days decays to 144 praseodymium, 17 minutes, which decays to 144 niobium, which is stable. Another example is 137 cesium, 30 years, decays to 137 metastable state, barium, 2.5 minutes, decays to 137 barium, which is stable. You can see here, in this case, the parent is very, very large, long-lived compared to daughter. And therefore, the parent activity, daughter activity becomes equal to parent activity once the equilibrium is established. But in the case of daughter being long-lived than parent, or parent being short-lived than daughter, then there is no equilibrium established. So you will find many such cases. For example, 138 xenon decaying to 138 cesium. So they are nearly same half-life. So you will not see an equilibrium. Instead, the activity of parent will decay. After some time, the daughter also will decay. Okay. So this transient equilibrium I have illustrated using this figure. That is, if you have a freshly purified parent isotope, this green graph, which is showing parent decay, if you have a freshly purified parent activity, then in that parent activity, the daughter activity will grow. And so the total activity will start growing, and after some time, when the steady state is reached, the total activity will decay with the half-life of parent. So why it happened? Because when the parent is decaying, the daughter is growing in that sample, and so the growth of the daughter leads to the growth of total activity, and the daughter activity in fact grows and it becomes more than that of the parent, but after the steady state is reached, the daughter also decays with the half-life of parent. How it has happened, I'll explain here. So this is the equation for the daughter activity as a function of time. Initial activity of parent into the lambda factor, lambda 2 by lambda 2 minus lambda 1 into e raised to minus lambda 1 t minus e raised to minus lambda 2 t. And so the total activity at any point of time is A1 plus A2. So this is the A1 activity plus this is the daughter activity, so that you can explain total activity. But what happens when the time is large? When the time is large, for large time, this lambda 2 anyway is a higher quantity. So lambda 2 becomes a very large quantity. So e raised to minus of a large quantity tends to 0 when lambda 2t becomes very large. And so you can neglect this term in this equation. And therefore, for large time, total activity becomes parent activity plus daughter activity. Two term has been neglected. So you will see here, both these terms have e raised to minus lambda 1t as a common variable function. And so you can club all of them together, A10, a constant k into e raised to minus lambda 1t. So you will find that the daughter activity also decays with the half-life of parent once the equilibrium is established. What I have shown here, the daughter decay, is that daughter which is separated from the parent when we prepare the freshly purified parent activity. So this is not the daughter activity which is decaying in the sample. This is the daughter activity which is decaying when it is separated from the sample. That is an important thing to know. So in transient equilibrium, you will see here, because of this factor, lambda 2 by lambda 2 minus lambda 1, this factor is more than 1. Because of this factor, the daughter activity becomes more than that of parent activity. So this is the parent activity, this is daughter activity. The factor k is more than 1. So this is the explanation why in transient equilibrium, the activity of daughter can become that more than that of the parent. Now, this is a great advantage in the case of nuclear medicine. One of the examples I have tried to explain the applications of that transient equilibrium, where 99 molybdenum having half-life of 66 hours decays to 99 M technetium having the half-life of 6 hours. You can see roughly the parent activity is about 10 times that of the daughter. And so you can in fact find out when this activity of daughter will become maximum. This activity of daughter A2, when it will reach maximum. So if you differentiate this activity of daughter with respect to time and you make it equal to 0, you will find Tmax. The Tmax is given here. Tmax equal to 2.303 by lambda 2 minus lambda 1 log lambda 2 by lambda 1. So you will find, like in the case of technetium 99M, after about 30 hours, the daughter activity will reach maximum. And this is the decay of molybdenum 99 having half-life 66 hours. Within 24 hours, technetium activity will reach maximum, and you can have a generator system where technetium can be milked from this parent, and you can utilize this for the nuclear medicine applications. Activity of technetium becomes 0. Next day, again the technetium activity grows up. Again, it reaches maximum. Again, you can separate it and do it for diagnostic applications. Third day, fourth day, and so on. Like this, for about a week, we can continuously milk technetium 99M from molybdenum 99 and use it in hospitals for diagnostic applications. So this is the advantage of transient equilibrium, where you use a generator system to produce the daughter activity and use it for your applications. In the case of secular equilibrium, what happens? I just go back to this equation. In the case of secular equilibrium, this factor lambda 2 by lambda 2 minus lambda 1. Now lambda 2 is much larger than lambda 1, and so lambda 1 can be neglected with respect to lambda 2, and so lambda 2 by lambda 2 becomes 1. So you will find that activity, total activity will become parent activity plus daughter activity, both activities will be same. So in the case of secular equilibrium, where lambda 2 is much larger than lambda 1, the activity of daughter becomes equal to that of parent, and that is why you will see here you have a parent which is having very long half-life. So over a period of our observation, let us say cesium 137, 30 years. So if you do the measurements for a day, activity of parent will remain constant, it will not decay. But if you have a freshly purified cesium 137, then the barium 137M will start growing and reach a maximum in a very short time. The half-life is 2.54 minutes. In about 4 half-lives of this one, about 10 minutes grow, and the activity of daughter will become equal to activity of parent. So you can see here that daughter activity grows and becomes equal to that of parent. Total activity will grow and become double the parent. So this is the advantage of secular equilibrium. There are many cases like strontium 90 decaying to yttrium 90. Yttrium 90, you can go on milking from strontium 90 over many years. So this is what I thought that I can explain the applications of this parent-daughter relationship, which find a lot of applications in nuclear medicine and many other cases. One of the applications of like this, as I was mentioning, this strontium 90, yttrium 90. Strontium 90 is 28.5 years and yttrium 90 is 64 hours. So if you have a column where you hold the strontium 90 and then you can milk it, yttrium 90 you can milk from that, and now yttrium 90 is 64 hours. So let us say some about 3 days. So in about 12 days, again you will have equivalent amount of yttrium 90 in the column, and you can go on milking, use it for therapeutic applications. Now I would like to stop here because the